This video will help with graphing a logarithmic function and finding its domain and range. So, a logarithmic function with base b. Again, we're going to spend a little more time on this in class and figure out a little more about what this really means. But for our purposes, with graphing these guys, what we need is a logarithmic function with base b has the form f of x equals log base b of x. Again, this is read log base, oops, sorry. Let me actually write this out the way you would read it. Log base b of x. That's how we would read that. And the big thing that we need here for today is that a logarithm is the inverse of an exponential. That's really what we're going to be using today. Because a logarithm is the inverse of an exponential, if y equals log base b of x, that's the same thing as b to the y equals x, because this is x and y switching places from our exponential function, right? Our exponential function is of the form y equals b to the x. If you switch x and y in that equation, x would come down here, the y would go up to the exponent. A logarithm is the inverse of an exponential function. So if kind of this notation right now doesn't make a whole lot of sense, we're going to solidify that in class. But for our purposes today with graphing, the biggest thing that we're going to be using is that a logarithm is the inverse function of an exponential. And because a log is the inverse of an exponential, the base of our logarithm is the base of an exponential, because the base of an exponential needs to be a positive number that's not equal to 1. Same thing here. So I'm just going to add where b is a positive number and it can't be 1. And because the range of an exponential, this value right here, had to be greater than or equal to, had to be strictly greater than 0, right? The things that came out of an exponential function, our range was 0 to infinity. The things that go into your logarithm are actually the things that came out of an exponential, and that means x has to be strictly greater than 0 when we are dealing with logarithms. Okay, so that's really what a logarithm function is. Again, the biggest thing that we're going to be using right now is that a log is the inverse function of an exponential. And this video is going to be focusing on graphing logarithms. So a logarithm is the inverse of an exponential. The base of the logarithm tells us the base of the exponential that it undoes. And so basically what that means is that if I have log base 2 of x, it is the inverse function of y equals 2 to the x, the exponential function with the same base. So if I wanted to graph y equals log base 2 of x, this is the inverse function of y equals 2 to the x. Well, I know what inverse functions, I know how to get the graph of an inverse function. We did this in class. You're going to switch x and y because that's what an inverse function does. It switches x and y. So I'm going to start with the exponential, the graph of the exponential function 2 to the x. We just covered this in a previous video, so feel free to watch that one if um, if you would like, I'm going to get a couple of points on my exponential graph. So if x is -1, then 2 to the -1 is 1/2. Again, we've done this in a previous video. A negative exponent gives you a reciprocal. I don't want to spend too much time on that. There's another video that can help with that. If x equals 0, then 2 to the 0 power is 1. And if x is 1, y is 2 to the first power, which is 2. So I have the ordered pairs -1, 1/2, 0, 1, and 1, 2 on the graph of y equals 2 to the x. Okay, but I'm not here to graph exponentials. I'm here to graph logarithmics. So to graph y equals log base 2 of x, that's the inverse function of this. So because I had the point 1, 2 on my exponential graph, that means 2, 1 is going to be a point on my inverse function. Again, switch x and y. Because 0, 1 is a point on my exponential function, switch x and y. 1, 0 is going to be a point on my logarithmic function, the inverse of the exponential. Because -1, 1/2 is a point on my original exponential function, then 1/2 -1 is going to be a point on my logarithmic graph, which is the inverse function. So with these 3 points, you can actually see this is what my graph of a logarithm is going to look like. Now, exponentials had a horizontal asymptote. I don't know if you recall that, but that horizontal asymptote actually becomes a vertical asymptote for our logarithmic function. So we have a vertical asymptote at x equals 0 for y equals log base 2 of x. Okay. Now, what if I wanted to graph y equals log base 1/2 of x? Well, I'm going to start with the exponential function, which is 1/2 to the x power. This is my exponential function that's the inverse of this logarithm. And I know how to graph this. It's easier to find points here. So I'm going to start with these guys. So if x equals -1, then y on this exponential function is going to be 1/2 to the -1. Again, that is 1 to the -1 over 2 to the -1. Both the 2 and the 1 will move, and we've got 2 over 1, which is 2. If x equals 0, then we have 1/2 to the 0 power, which is 1. And if x is 1, then we have 1/2 to the first power, which is 1/2. So my original graph goes through -1, 2, 0, 1, and 1, 1/2. That is the exponential function here. Go, looks something like that. That's my exponential function, y equals 1/2 to the x. Well, my logarithmic function, y equals log base 1/2 of x, is going to be the inverse of this. So I'm going to switch x and y because that's what inverse functions do. So instead of this point -1, 2, I'm going to have the point 2, -1 on my inverse function. That's the point 2, -1. Instead of the point 0, 1 on my original function, I'm going to have 1, 0 on my inverse function. Switch x and y. And instead of the point 1, 1/2, I'm going to have the point 1/2, 1 on my inverse function because we switch x and y. So these red ones are the points on my logarithmic function, my y equals log base 1/2 of x. And if I connect these, this graph is going to look something like this. Okay. There is y equals log base 1/2 of x. That's what my log function looks like. I didn't label the one in the previous one. This was y equals log base 2 of x. My previous one. Sorry about that. And again, this one, instead of having the exponential has a horizontal asymptote, this log base 1/2 of x has a vertical asymptote that it approaches up here at the top. And that vertical asymptote is x equals 0. Okay, so those are what logarithmic functions look like. So some characteristics of logarithmic graphs: log base b of x. Oh, I didn't go through the domain and range of these guys. Sorry, y'all. Let's try this again. So let's come back here. Again, we are looking at log base 2 of x, which is this red one right here. What's the domain of that graph? The x values that are covered. Well, this goes forever over here, so that's going to cover all of the x values up to infinity. And my x values are covered down to, but not including 0, because this vertical asymptote at x equals 0, we're never actually going to get to x equals 0 and touch it. So this is a parenthesis right here. And we don't have any graph over on the left side, so we won't have any negative x values covered. And the range of this thing, what are the y values that are covered? Well, this goes all the way down to negative infinity. And this is going to continue up and to the right forever because it continues up forever. Sorry, I closed that, but I shouldn't have. This, excuse me, this goes all the way up to positive infinity. Sorry about that, guys. And my iPad is freaking out a little bit. Okay. Okay, let's try this again. There we go. Got it. Okay, so our range is negative infinity to infinity. All of the y values are covered. It's going to take us a really long time to cover all the way up to y equals infinity, but eventually it'll get there. Okay, and then this log base 1/2 of x, this guy right here. Again, the domain of this 0 to infinity is covered. 0 is a parenthesis here because, again, we have an asymptote we are never actually going to get to and touch x equals 0. In our range, the y values that are covered go all the way from negative infinity to infinity. It's going to take a real long time to get down here to negative infinity, but it's going to happen eventually. Okay, so those are our graphs of y equals log base 2 of x and y equals log base 1/2 of x. Generally, if we have y equals log base b of x, our domain is going to match these two. Your domain is going to be 0 to infinity. Your range will be negative infinity to infinity. And again, these are for your basic untransformed functions. Your domain and your range might change a little bit based on transformations. So make sure that you pay attention to your graph when you're filling in domain and range. These guys have a vertical asymptote. The vertical asymptote happens at x equals 0. And if your b value is greater than 1, like it was over here, log base 2 of x, we are increasing left to right. graph increases from left to right. There's no name for this one with exponentials. We call that exponential growth. We don't have logarithmic growth and logarithmic decay. That's not really a thing. These don't have names the way that exponentials did. And if our base is between 0 and 1, if it's a fraction, like here with the log base 1/2, notice that our graph decreases from left to right. So that's kind of what these log graphs are going to do. Okay, now again, we can have some transformations of these guys. Transformations that we can do is we could put a negative out front. We could add or subtract a number inside the logarithm with x, and we might add or subtract a number outside of the function. And we have programming to know what these guys do. So if you have a negative out front, then you will, I'll say, flip the graph upside down. Over the x-axis. You'll flip it vertically over the x-axis. If you add or subtract an h inside with x, this is going to shift you left and right, and it's going to go the opposite way that you think it will. So if you subtract h inside, then that shifts the graph to the right h units. And if you add h, that will shift your graph to the left h units. It's going to go the opposite way you think it will. And if you add or subtract a k to the outside, that's going to shift you vertically up and down. And this is going to move the way that you think it will. If you add k to the outside, it will shift your graph up by k units. And if you subtract k from the outside, that shifts your graph down by k units. So this one has a vertical asymptote, right? These log functions have vertical asymptotes here at x equals 0. Which transformations here will affect your vertical asymptote? Well, if you take this whole thing and flip it upside down, your vertical asymptote stays in the same place, so that won't change. If you shift this graph up and down, your vertical asymptote, if it moves up and down, it stays in the same place. What if you shift your graph left and right? Then your vertical asymptote would move with your graph. So I'm just going to make a note here that your vertical asymptote shifts left and right with your graph. So for instance, if you move your graph to the left by 3 units, then your vertical asymptote would move from x equals 0 to x equals -3. You would move it left 3 units. And again, we are going to note that order matters. When you are transforming graphs, the first thing that you're going to do is shift your graph to the left and right. Second thing that you're going to do is flip it upside down if you need to. And the very last thing that you're going to do is shift that thing vertically up and down. All right, so let's practice this thing. Okay, so again, we're going to list the transformations in the order that they would be performed. So if I wanted to graph f of x equals log base 2 of x minus 2, we aren't asked to do this, but the graph that we would be transforming is the base graph. So if we remove any transformations that appear here in our function, what we would be left with is log base 2 of x. This is our base function. And we know what that looks like. We just graphed it up here. Log base 2 of x is here. It increases from left to right. And our base function looks like this. And so, excuse me, that would be our base function. What transformations have to happen to make it look like this? Well, the transformation that appears here comes from this minus 2. And that is being subtracted inside with x. That's going to shift us right and left. It's going to go the opposite way you think it will. So this is actually going to shift our graph to the right by 2 units. And that's the only transformation here. So that's the only one I'm going to do. All right, number 2. G of x equals log base 2 of x minus 2. Okay, again, our base function, if we got rid of anything that makes a transformation, we would be left with y equals log base 2 of x, which is this increasing logarithmic function here. And the transformations that we have here come from this minus 2 outside, and that is going to shift us down 2 units. That's the only transformation, so that's the only thing we have to do. All right, how about if I have h of x equals 1 minus log base 2 of x? This looks a little different than this because we always start with the log first, and any other numbers being added or subtracted are written on the right. So I'm just going to reorganize this. The negative stays with the log since it's negative. So I'm just going to rewrite this into negative log base 2 of x plus 1. The log is negative, the 1 is positive. So I can rewrite it like this. Again, if you get rid of anything that makes a transformation, our base function is y equals log base 2 of x. And the things that cause transformations are this negative out front and this plus 1 here. This negative out front will flip us upside down. And this plus 1 out here on the end will shift us up 1 unit. Order matters, so what am I going to do first? I'm going to flip upside down because you have to move up and down last. Okay, so we're going to flip upside down over the x-axis first, and then the second thing that we're going to do is shift the graph up 1 unit. All right, last one. K of x equals log base 2 of x plus 5 plus 3. Okay, again, our base is y equals log base 2 of x. The things that cause transformations here are the plus 5 and the plus 3. The plus 5 is inside with x, so that's going to shift us right and left. And that's going to go the opposite way you think it will, so that's going to shift us to the left 5 units. And then this plus 3 is outside, so that's going to shift us up and down. And that's going to go the way you think it will, so that's going to shift us up 3 units. Order matters, so we're going to go left 5 first, and then we're going to go up 3 next. All right. Now we actually want to use the information that we have above to graph log base 2 of x plus 5 plus 3. So we just actually went through this one right here. So I know that I'm going to take the base graph of y equals log base 2 of x. And I'm going to take that graph and I'm going to shift it to the left by 5 units and up 3 units. So let's start by graphing our base function of y equals log base 2 of x. We just did this a few minutes ago. Y equals log base 2 of x is here. And we'll have the point, I'll just do 2 points here. 1, 0, and 2, 1 were on this graph. So I'll just start with those. So 1, 0, and 2, 1 were nice points on this graph. And so here is my log base 2 of x. That's my base function. So now I'm going to take this function, and I'm also going to make sure that I put in my vertical asymptote here. And then I have to shift this thing to the left by 5 units first, and then we will go up. So the first thing that I'm going to do here is go to the left by 5 units. So I'm going to take each of these points and go left 5. So 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. So notice this looks like this. Now, when I shift this to the left, notice that my vertical asymptote is going to shift with the graph. So my vertical asymptote moves with the graph over here. My vertical asymptote is now at x equals -5. And then the last thing that I have to do is shift this thing up 3 units. So I'm going to take each of my points and go up 3 units. 1, 2, 3. 1, 2, 3. And here I have my final graph. And so since that's the last thing that I had to do, I'll put my points in. I've got 4, 3, 3, 4. It looks like this. And my vertical asymptote here is x equals -5. That's my final graph for y equals log base 2 of x plus 5 plus 3. All right, so I hope that helps with the graphing logarithmic functions and finding their domain and range. And I will see you next time.